So Rick O'Connor, who's also the RISC-V Foundation Executive Director, he's going to give a talk on his other day job, running RapidIO.
Yeah, I think I'll just use this guy. You guys can hear me? So yeah, a bit of a change of pace from some of the other presentations, and as Krista said, I'll be the initial executive director of the RISC-V Foundation as we get that off the ground. So it's pretty exciting. And so why am I here? Well, one of the reasons is Krista and his team have been looking at different ways of building out larger RISC-V based systems and clustering RISC-V and maybe together with other accelerators in a heterogeneous cluster. And RapidIO is a technology that does that very well. So Krista invited me here to give an update to this community on what RapidIO is and where it's used and so on. And RapidIO is also a nonprofit 501c6 open standards body development organization, and that was part of the reason where he was like, hey, you know, we need one of those for this RISC-V thing. So those are really the two reasons why I'm here. So before I get started though, show of hands, how many people have heard of RapidIO before they read the agenda today? So that's good. So now you get to keep your hand up. How many people here have read the RapidIO spec? A few less. How many people here have ever implemented a system, chip, FPGA, software drivers, anything related to RapidIO? Me, a guy from Texas Tech? Right on. Well, there you go. So this might be a helpful discussion then. Okay. You have the slides, so I'm not going to go through all of the slide deck, but I wanted to have a complete set of information for you so that you'll be able to maybe refer back to this, and obviously you can reach out to me if you have any questions. But notionally, what I've got broken down here is a little bit of an overview of the technology and where it's been, some of the markets that it's used in, and some of the committees or task groups that we have in flight with some of the work that's being done within the organization. So here's something that always gets people's attention. There are more 10 gigabit per second RapidIO ports on the planet than there are 10 gigabit per second Ethernet ports. And that is, people go, really, what's he smoking? And the reason for that is wireless infrastructure. So in the cellular infrastructure space, not on the cell phone, but in the gear that's at the base of a tower, base stations, for 4G and LTE, RapidIO has 100% market penetration in those systems. And whether that's Ericsson, Nokia, Alcatel-Lucent, Huawei, ZTE, Great Dragon Telecom, all of that infrastructure gear, if I call you from my 4G LTE phone, and we're not in the same room, it's more interesting when there's two towers involved, and wherever you are in the tower that's next to you, and you answer on your 4G LTE phone, that call will go through two sets of base station electronics at the base of the towers that are connecting our phones, and or data if we're transmitting data to each other, and that will go over a RapidIO fabric. And what's interesting is, unless you're in that space, you would have told me I was, like I said, what is he smoking? 10 gigabit Ethernet is obviously a great technology. It's used in data centers quite a bit, but when you think about it, how many data centers do you drive by, depending on where you live? But how many data centers do you drive by on your way to work compared to how many cell towers you drive by? So for 4G LTE rollout, it's 100% market penetration. For 3G, which is obviously a little older technology, outside of China, where it's 100% market penetration for 3G, it's about 60% market penetration in the rest of the world. And so as a technology, it's very well established. It's a proven technology. It's been in the market for a long time. And what it really accelerates at is clustering heterogeneous computing resources for performance-critical computing applications. And when you think about a cell call, when that antenna data, that airwave data is at the tip of the tower, you have a finite latency budget within which to process it and do something with it, because you don't get to ask for the data again. right? When that airwave data is gone, it's gone. So there's a very finite window within which to process that data, and that's the bulk of where RapidIO is used and why it shines. Unlike things, well, I'll talk about how it compares to other technologies. Technology has been around for quite a while. The foundation or the organization was created in like 99, 2000, and has evolved since that time. The people who were involved back then did a very good job at creating a layered specification stack. So the PHY layer can evolve independent of the transport layer and the logical layer. One of the things that's interesting about the technology is it's not a software-based protocol, right? All transactions are terminated in hardware. And in fact, the origins, Motorola semiconductor product sector, the ancestors to Freescale, were one of the original authors of the spec. And another show of hands, who remembers PowerPC? Wow, that's pretty much everybody. That's good. So back in those days, there was these 60X devices that both IBM and Motorola were working on, and the front side bus was a multi-drop bus then, the 60X bus and MPX bus. As those multi-drop buses were running out of steam, the notion was you're going to replace them with point-to-point fabric-like things. So RapidIO actually originated as a replacement to the MPX 60X multi-drop bus. So it can do things that you would expect to be able to do in a processor bus, which is why some of the RISC-V community is interested in it. In fact, it's unfortunate the IIT Madras guys couldn't be here today to talk to you about the projects that they have underway, because they have like 4 or 5 different processors they're working on that are 6. They have 6. They should have 5 RISC-V processors just for, but apparently they have 6. And they're using RapidIO as, if you will, the front side interface on those processors. And many of the things that you'd want to be able to do in a processor bus, like atomic transactions and twiddling bits and registers in the other part of the system, are supported by RapidIO. So I always get asked, okay, yeah, but I've never heard of it, so how's it compared to Express or Ethernet or InfiniBand? So here's a 10,000-foot view, sort of Reader's Digest summary of how it's the same or different. The thing to really take away is Express and RapidIO are both hardware-terminated protocols, right? No stack. You don't need a processor or a host bus adapter running TCP or an InfiniBand protocol stack to terminate a transaction. The biggest difference between something like Express and RapidIO is the origins of Express are PCI, right? A multi-drop peripheral bus, right? So you have a host processor sitting up here, that's probably IA-based, and it's God. Back in the day, it was attached to a host bridge, a north bridge, and then that was attached to a south bridge, and all the peripherals sat down below on a peripheral bus, PCI, and those peripherals were subservient to the host, right? North-south based communication paradigm, not a true peer-to-peer, any processor to any processor. In RapidIO, there is no notion of a host. At power-up, there's discovery that has to happen, and transactions go out to enumerate all the devices in the fabric and so on. But after that has occurred, there's no such thing as a host in a RapidIO system. It's a true peer-to-peer fabric. Pretty strong ecosystem, lots of interesting companies. A logo that is in the process of being put on this slide is the Aspire Lab here at Berkeley. So that's one of the other reasons why I'm here. And we have a lot of activity within the ecosystem at the chip level, at the system level, and at the software level. And like I said, it's been in production for a long time and is very well supported. one of the things that's interesting from a networking standpoint, and certainly, when I was fresh out of school, which is a few years ago now, the notion of this converged networking compute thing was happening back then. It actually probably is getting closer and closer to happening, in that the kinds of architectures that you want to have at the edge of the network are actually, other than scale, they're not that dissimilar from the kinds of the the kinds of the architectures that you want to have either in a data center or at the center of the network. I'll show you what that looks like over here, right? So having, other than size and power, having processing resources, storage resources, and acceleration resources at the edge and at the mobile end of the network, right through to the data center, other than the power budget that you've got and space budget that you've got, there's not really a lot of differences from an architecture perspective. And arguably, power it's always been a concern on the embedded side, but power is an increasingly larger and larger concern on the data center side, as we know. So if you look at it pictorially this way, from an access right through to the cloud and server side, and you sort of generically think about processing, storage, acceleration, and networking as building blocks that if you could scale them and hit the right price, performance, and power budgets along the way, wouldn't it be nice if you had a single architecture that could go up and down that scale? Well, certainly RISC-V, I think, has the potential and promise to be able to do something like that from an ISA standpoint. And from a fabric and an interconnect perspective, RapidIO very much has that capability at the heart of its specification. So some markets. Definitely interest in the data center and HPC space, and primarily from the standpoint that as we are all convinced that the performance gains of Moore's Law is kind of, we're hitting our head up against the ceiling on that one. People are starting to increasingly talk about gaining performance out of better architectures or different architectures, and heterogeneous clustering being one of those. We have a very active task group, which I'll talk about in a moment, looking at using the AXI, ACE, and AMBA, the AMBA environment with AXI and ACE. You guys know what I'm talking about here, the SoC, okay. And scaling those coherent transactions out across RapidIO. And if you paid attention to the spec stack here earlier, there in the logical layer, right in the center up here, there's a globally shared memory spec that has been part of the RapidIO stack from its inception. It's a CC-NUMA-based coherence protocol that was built into the original set of standards that were released at the very beginning. I don't think anybody ever built a device that implemented it, or if they did, they didn't really see the light of day. And we're cracking the lid on that spec and looking at how to map the AXI and ACE protocols across that specification now. And we'll talk about that more in a little bit. But one of the more public implementations of a data center application that uses RapidIO is a platform called the HP Moonshot, in particular a cartridge that HP has called the M800 blade. And it uses a set of Keystone 2 TI processors that has 4 A15s and an octal set of C66 DSPs per SoC, 4 Keystone 2s per cartridge, and that gets you, 720 A15 cores and 14 some odd C66 cores, all connected together on a 2D RapidIO torus. So it's a pretty interesting heterogeneous architecture, and I don't think I have it in this slide deck. No, I don't. But there's some info on the RapidIO site if you want to go and look at a white paper from PayPal where they use this platform for fraudulent transaction detection. So if you compare that to a cell tower processing airwave data, you go, well, what do these two applications have in common? In financial transaction space, latency equals dollars, right? The longer you take to detect a fraudulent transaction, the more money you're leaking out the door. right? So it's clearly a different application, but it's a performance-critical computing application where latency is king. We've already talked about 4G LTE and the millions of RapidIO ports, for instance, so I won't spend any time here. Industrial automation and high-end computing on production floors. Anybody here know who ASML is? Those of you that are reasonably close to foundries would know them. So they probably have maybe 70 to 80% market share of wafer processing equipment, right? So every major foundry on the planet uses ASML gear in some way, shape, or form on their wafer ASML, yeah, on their wafer lines. All of ASML gear is RapidIO based, and they have probably 5 or 6 subsystems. Their wafer processing gear is like the length of a table and maybe 2 or 3 rows deep, right? It's a big honking machine, and there's 6 or 7. I think it's actually 6. There's 6 different racks of embedded computing electronics in those systems, controlling how the reticles are being dispatched, what the temperatures are, the exposure time, and so on. So it's a very large real-time compute and control system, and that's all RapidIO based. Mil-Aero is another interesting, not necessarily high volume, but very demanding set of applications for where the technology is used, right? So all this to say that there's at least four very interesting markets that continue to attract the use and the benefits of RapidIO, and I think the complement with the RISC-V stuff is actually pretty interesting. Doing all right. So the next few slides, just to give you a feel for some of the activity that's underway within the different task groups within the community. So I talked a little bit about this already, and this is around scaling 64-bit ARM processors coherently across a RapidIO fabric, and it's not just about like a 2P or 4P, SMP machine or anything. It's really most of the work and discussion is around connecting to accelerators, right? Whether they're FPGA, accelerator algorithms that are embedded into an FPGA, or whether you've got DSP through GPU clustering or DSPs, very much like the Keystone application that I talked about earlier. It's really around those heterogeneous clusters and having a true peer-to-peer architecture and fabric. So here's some of the companies who are involved in that work. Most of these companies were already ARM licensees, ahead of this work being started, if not all, except I guess for those of you that don't know, that's the logo for the IIT Madras guys that are doing the 6 RISC-V architectures. So it's a pretty healthy group, and it's a pretty interesting set of discussions. This is a little hard to read, but you've got it in the material to be able to download afterwards. This is a use case where most of the discussion in the group has taken place is around identifying the use case scenarios that we're, in terms of the problems that we're really trying to solve. And it's really around, get the numbers right, like 3 to 6 or 7, those use cases in the middle, right, where we're clustering heterogeneous number of sockets either on a blade or certainly within a shelf, a few blades within a shelf. Another interesting task group is an open source software initiative around kernel enhancements, fabric management stack, and then data plane or data path extensions for RDMA sockets and MPI. So it's a very active task group. I don't have the members who are participating in this, but it's most of the guys from that previous slide, as well as some systems guys So very much, what we're doing is the yellow, is the yellow one yours? The yellow blocks is what the group is working on, and this is pretty much, it's time to shoot the engineer. We're pretty much at a point 0.9 and holding dot release, right, for the initial release of the code, and it seems like we've been there for a long enough period of time that I think in order to be done, we just got to tell them, okay guys, we're finished, let's release the stuff and get it out there. And we've also got an open source bus functional model that we're working on, and whether this group continues or not, most of the SoC vendors who have participated in this work in the past are increasingly relying on third-party IP, RapidIO IP vendors, and not doing any of their own specific IP development. So they're looking at, well, I don't need to participate in this open source plus functional model anymore. I'm just going to shoot my IP vendor if it doesn't work. So this, to be honest, is a task group that I'm not quite sure if it's going to continue on in its current form. And we've got a 25 gig per lane or 100 gig per port. Most RapidIO ports are by 4 wide. And this is being worked on two fronts. One for short reach in that sort of 2P, 4P coherent scale out model I talked about earlier. And then one for longer reach going off card and board to board and so on. And I think that's it. So we can debate all of these facts that I put up at the beginning if you want, or I'm happy to take any questions.
Hi, Rick. Yeah, I'm George from Intel. I'm the RapidIO of how long you build your ecosystem and what effort you take to build this ecosystem for RapidIO, such huge penetration at telecom.
So I think if I've got your question right, it's how long did it take to build the ecosystem?
Yeah, what you did.
Yeah, so I think the initial deployments around sort of Gen 1 were probably, I'm going to say 3 to 5 years, somewhere in that range after the spec was initially released. And when you think about, it was the wireless infrastructure space that drove the standardization of RapidIO to begin with, right? So I had a semiconductor startup that was part of it at the beginning. So that's the worst possible space to be in when you are on the front end of ultimately selling to the telcos, right? Because as you know, if I'm starting a chip today and all I've got is ideas on a napkin, my napkin to silicon at best is probably an 18 to 24 month journey, right? So then at the end of my 24 months, say, you've got a piece of silicon now in, say, Ericsson's hands, and they're starting to build out a prototype system for their own internal testing. Maybe they started ahead of time in anticipation of when my prototype silicon, first silicon is going to show up. So let's give them the benefit of the doubt that they started early, and that'll take another year for them to get a system out for field trials. And that's probably fast. So now we're at 36 months. And field trials have started. So now they're doing field trials with, pick your favorite local Sprint or AT&T or whatever. They're doing field trials with a telco. And that field trial set will take, at best, earliest 6 months, but probably more likely 9 to 12 months. So now we're 48 months into the journey. And then the field trials that the telco is doing will have produced a result, and they're ready for full-scale deployment. And by the time when they push that button, their volume ramp for that full-scale deployment is arguably another 12 months. So now we're at 60 months, 5 years, before everybody starts to get paid. Okay, so it was in that kind of range of 3 to 5 year. So anybody who's thinking about doing some IP or startup activity around any of this technology, and you think you're going to go target telco space or any big iron, even fast-moving data center space. It's not a year, it's not two, and it's probably somewhere 3 to 5. Just I got the body scars to prove it. That answer your question?
Yeah, Carl. I also see the system maybe on the library, IP, on driver, and all these things. Do you provide all these, all your partner provide these, why do you provide this?
So I think the question there was drivers and IP for libraries and so on. A lot of that came after the initial deployments, right? The initial stuff was purpose-built, developed for handfuls of guys that were building those systems. And then as it attracted more and more, as the volume became more obvious and it attracted more vendors, then you have the slide that I showed with all those logos. And it took some time. It's not an overnight kind of thing.
Rishir Nikhil from BlueSpec. Regarding the coherent scale-out, you had ARM CHI-5. Is that open or not? And how does that fit into your charter?
That's a really good question. So no, it's not. And so the question was, how does the coherent hub interface, AXI-5, fit into the open part of the charter? So the AXI-4 is ACE, right? And ARM's looking at what they're going to do with 5, but so there's folks from ARM who are basically there to keep everybody, keep us from painting ourselves into a corner. So the work that we're doing is based on ACE and AXI-4, and obviously the individual members, the individual companies who are party to the AXI-5 license know what's there. ARM themselves obviously quite clearly knows what's there. And any work that we're doing in that spec that is going to get us painted into a corner and not compatible with, they just say, let's go over here, let's go over here. And we don't really know why.
Same problem, unaffiliated. How easy would it be for someone who has no professional contacts, who has no resources to make use of RapidIO? For example, I'm building my own computer. What if I want to use RapidIO in my own design?
Go right ahead, download the specs and use away.
Okay, maybe I didn't phrase the question correctly.
You don't need to be a member to access any of the specs.
Okay, but what's the implementation complexity? Like, how many lines of code of Verilog am I looking at?
So depending on what you wanted to implement,